Hey everyone, welcome back to the Systems Podcast, the show where we break down the systems behind modern software, startups, AI, infrastructure, and engineering at scale.
Whether you're a software engineer, founder, student, or just someone obsessed with how complex systems work, you're in the right place.
Let's get into it.
So today we are jumping into a deep dive on a topic that is honestly just completely fracturing how we think about data centers.
Yeah, we're unpacking a really fascinating presentation from Cisco's Richard Lakin.
Right.
And the mission here today is to really understand how artificial intelligence is just breaking traditional network architectures.
Oh, completely breaking them.
And, we also want to look at the incredibly complex physical systems that engineers are building right now to fix it.
Yeah, and to really grasp why these networks are collapsing under the weight of AI, you have to look at how AI itself has shifted.
Right.
Specifically, this transition to what we call agentic AI.
Because older AI, if you look at it, it was mostly just prompt and response, right?
Exactly. You ask a large language model a question, and it spits out text based on its training data.
Which is pretty predictable traffic.
Right. It's very linear. But agentic AI it's a completely different beast.
How so?
Well, it's designed to observe, to reason, and then to act autonomously.
Oh, wow.
Yeah, so it performs these multi-step tasks like cross-domain correlation or writing and executing its own code to solve a problem.
Or even like autonomously triaging a network outage on its own.
Exactly, and that fundamental shift in the software behavior from just fetching an answer to actively reasoning through a problem, it triggers a massive shift in the physical network traffic underneath it.
Right, because if you manage a network today, you were probably used to optimizing for north-south traffic.
Yes, the classic enterprise model.
Which is just data moving from your servers out to the internet and then down to the user screen.
Right.
But these agentic AI models, they require thousands of GPUs to constantly synchronize their parameters and their weights with each other. So they're talking sideways, which creates this absolute explosion of east-west traffic.
It is a total flood of server-to-server communication.
Okay.
When these AI clusters run operations like what they call an all-to-all or an all-to-reduce synchronization,
Okay.
every single GPU in that cluster needs to exchange its computed weights with every other GPU.
At the exact same time.
Essentially at the exact same millisecond, yeah.
Okay, let's unpack this with an analogy because think of traditional data center traffic like a morning commute.
Okay, I like that.
You've got lots of independent cars, right? And they're all filtering through city streets, going to different destinations.
Sure, very predictable flow.
Right. But this AI training traffic,
Yeah.
especially those all-to-all operations, it's like 1,000 massive freight trains all trying to cross the exact same intersection at the exact same millisecond.
That is a terrifying image, but it's incredibly accurate. And those freight trains represent what network engineers call microbursts.
Microbursts.
Yeah. Because when thousands of GPUs share their data simultaneously, they flood the switches with these microscopic but massive spikes of data.
And if the hardware can't absorb that burst,
Then packets of data just get dropped.
which in a normal network isn't a huge deal, right?
No, a dropped packet usually just means a slight delay while the server resends it.
Right.
But in an AI training cluster, a dropped packet is a literal train crash.
Wow.
The entire synchronization cycle just stalls out waiting for that missing data.
So all the other GPUs are just sitting there waiting.
Exactly. And that introduces jitter, and jitter will absolutely destroy your job completion time.
Because time is literally money with these things.
Huge amounts of money. A training run that should take, say, a month could stretch into 3 months just because of network jitter.
Okay, so if dropping a single packet derails the entire training job,
Yeah.
why is there this massive push in the industry right now to build AI backends on Ethernet?
Right. The great protocol war.
Because historically, Infiniband was the undisputed king of backend AI connectivity, exactly because it doesn't drop packets. It's a natively lossless protocol.
It is. But Ethernet, by its very design, it just drops packets when a switch gets congested.
Right. So why force Ethernet to do this job?
Well, it all comes down to operational reality, honestly, and this deep desire for a unified standard.
Okay.
Organizations want to use the same operational models, the same monitoring tooling, and frankly, the same engineering skill sets across everything.
So their front-end networks, their management networks, and their back-end AI networks all running on the same logic.
Exactly. Ethernet offers this massive, flexible ecosystem that breaks the vendor lock-in you often get with InfiniBand.
But how do you actually teach a lossy protocol to be lossless? You can't just flip a switch and tell Ethernet to stop throwing packets in the trash.
No, you can't. You have to engineer Ethernet to mimic InfiniBand's lossless properties.
Okay.
And that requires a very specific mechanism called priority flow control, or PFC.
Right, PSC.
And you pair that with explicit congestion notification, which is ECN.
So how do those work together?
Think of PFC as a physical stoplight for the network.
Okay.
When a switch's memory buffer hits a critical threshold, let's say it's 85% full, it doesn't just quietly drop the next packet that arrives.
Right, which is what standard Ethernet would do.
Exactly. Instead, the switch generates a pause frame, and it fires it back upstream to the sending server.
Oh, wow. So it literally tells the sender to just halt all transmission.
For a few microseconds, yes.
So it forces the sender to hold its traffic until that intersection clears out.
Exactly. So PFC acts as the hard brake.
Got it.
And then explicit congestion notification, or ECN, that acts as the gradual throttle.
Okay, how does the throttle work?
When traffic starts getting heavy, the switch actually modifies the IP header of the packets passing through it. It flicks a specific bit.
Okay.
When the receiving server gets those marked packets, it realizes, hey, the network is congested.
Oh, so it tells the sender to slow down?
Exactly. It tells the sender to shrink its TCP window, effectively slowing down the transmission rate before the switch ever needs to hit the hard brake with a pause frame.
That is incredibly clever. But I imagine clever protocol manipulation isn't enough if the physical hardware itself is a bottleneck.
Oh, absolutely not. The physical silicon has to be designed to handle these microbursts, too.
Right, and the source mentions Cisco using this massive 64-port shared packet buffer on their silicon.
Yes.
Why a shared buffer? Why not just dedicate a specific slice of memory to every single port on the switch?
Because microbursts are totally unpredictable.
Yep.
If you partition your switch memory, so port 1 gets a rigid amount of space, and port 2 gets a rigid amount.
Right.
What happens when port 1 gets hit with one of those massive freight trains of traffic?
Its dedicated memory fills up instantly.
Yes, and it starts dropping packets, even if the memory pool for port 2 is completely empty.
Oh, I see. So it's just wasting capacity.
Exactly. A shared buffer takes all that memory and creates one giant communal pool.
So when a microburst hits a specific port, it can just dynamically borrow memory from the shared pool.
Precisely. It absorbs the shock, holds the packets, and prevents those drops.
And the scale of this hardware, it's just staggering. We are looking at switches that need to push 1.6 terabits per second.
Yeah, the numbers are wild.
And to pull that off, the industry is moving toward these 100 terabyte application-specific integrated circuits, or ASICs.
Single custom silicon chips.
But why is it so critical to keep all of that routing power on one single monolithic die? Why not just link a bunch of smaller chips together inside the switch?
It really comes down to the physics of latency and power consumption.
Okay.
Specifically, the power drawn by the serializer and deserializer components.
Right.
Every time data has to leave one chip, travel across a printed circuit board, and enter a second chip, you pay a massive penalty.
In both time and electrical power, I assume.
Yes, a huge penalty. By engineering a 100 terabyte ASIC on a single piece of silicon, the data never has to leave the chip to be routed. It happens at the speed of the silicon itself, which drastically reduces power consumption and keeps latency down to just nanoseconds.
This actually brings us back to a really fascinating detail from the presentation.
Oh, the 2019 switch.
Yes. Because I always thought of hardware as basically frozen. Like, you buy a switch, it does what it does, and then you throw it out and replace it.
That is how merchant silicon usually works, yes.
But the source mentions a customer taking a pre-pandemic 2019 switch and repurposing it for 2024 AI workloads.
Yeah, it's amazing.
How is that even physically possible?
The secret lies in highly programmable pipelines.
Okay.
Cisco's custom silicon, like their Silicon One architecture, relies on a microcode pipeline that isn't permanently frozen at the factory.
So it's more like software than rigid hardware.
In a way, yeah. So when this customer needed to handle modern AI traffic, engineers could actually develop mid-cycle features and push them directly down to the hardware level.
They literally taught a 5-year-old chip new routing tricks.
It really did.
And the specific tricks the source mentions are dynamic load balancing and packet spray.
Right.
Because in a normal network, standard routing protocols pin a traffic flow to one specific path, right? to ensure all the packets arrive in order.
Exactly. But AI generates what we call elephant flows.
Elephant flows.
Yeah,
Right?
these massive continuous streams of data that will easily choke a single 400 gigabit link.
So if you rely on traditional routing, half your network cables would be completely overwhelmed, while the other half just sit empty.
Exactly. So to fix this, you need flowlet distribution.
Flowlet. Okay, how does that work?
The programmable silicon is actually smart enough to monitor an elephant flow and look for natural microsecond gaps in the data.
Okay.
When it sees a gap, it splits the flow into a smaller chunk of flowlet.
Oh, I see.
And then it dynamically sprays those flowlets across every available path in the network simultaneously.
So the network just blasts the data out like a shotgun.
Pretty much.
But then the receiving network interface card on the GPU has to catch all those out-of-order packets and reassemble them instantly.
It does. It's an incredibly heavy lift. But because the pipeline was programmable, they could tune that 2019 ASIC to handle this packet spray.
That is wild.
The source also highlights an electric vehicle manufacturer that used this exact same programmability to run a unified network.
Oh, right?
They tuned the ASIC to simultaneously prioritize east-west AI traffic using flowlets, handle standard high-end storage traffic, and manage their general management network.
All in the exact same physical switch.
All in the same box.
Okay, so we have programmable silicon, we've got shared buffers, and lossless Ethernet protocols.
Yeah.
But physically arranging these switches inside a massive AI factory that requires a completely new blueprint.
Oh, absolutely. The traditional three-tier architecture is fundamentally breaking under AI workloads.
Because that three-tier blueprint relies on server racks connected to leaf switches,
Right.
which connect to spine switches, which all funnel up to a massive super spine at the top of the building.
And the latency math of a superspine just destroys AI job completion times.
Because of the extra hops.
Exactly. Every time a packet hops from a leaf up to a spine, up to the superspine, and back down, it adds nanoseconds of delay.
Which again, for web traffic, you don't even notice.
But for an all-to-all GPU synchronization, those extra hops create a massive bottleneck.
So the solution is routing around the super spine entirely.
Yes, by moving to a scale-out multi-plane design.
Okay.
Instead of building up into 3 tiers, engineers are building outward in 2 tiers.
And the breakdown of how this multi-plane design works is fascinating.
It really is.
Because you take an 800 gigabit network interface card, a NIC, sitting on an NVIDIA GPU.
Right.
And instead of sending all 800 gigabits down one fat cable to a single network fabric, they physically split the connection.
Yes, they run 2 dedicated 400 gig cables.
Okay.
One cable connects to network plane A, and the other connects to an identical, completely independent network plane B.
And they are active-act, all right.
Exactly. They are both actively passing traffic.
So think about the network architecture you might manage at work. If a core spine switch fails, you probably have a massive bottleneck or even an outright outage.
Oh, for sure.
But in a multi-plane design, it's all about containing the blast radius.
Yes. If someone unplugs a cable or an entire network plane crashes, the GPU doesn't even really notice.
It just keeps going.
Yeah, the AI collective simply stripes its workload across the surviving plane and keeps computing.
So it provides massive fault tolerance.
Massive. But orchestrating this architecture introduces a huge tension in the industry right now.
Tension over what?
The operating systems that actually run on these switches.
Ah, right. Because we have Cisco's proprietary NXOS on one side, and then Sonic, which is an open source network operating system, on the other.
Exactly.
So let me play devil's advocate here for a second.
Go for it.
Why is a massive hardware company like Cisco, a company that makes its money on vertically integrated systems, heavily contributing to the open source Sonic project?
It seems counterintuitive, right?
Doesn't that just invite hyperscalers to use free software on Cisco boxes?
It is a calculated trade-off driven entirely by the reality of hyperscalers.
Yeah.
Massive cloud providers demand Sonic. They employ armies of software engineers. They run heavily automated bespoke environments.
Right.
And they absolutely refuse to be locked into a single vendor's proprietary code.
So if you want to sell switches to a hyperscaler?
It has to run Sonic. Full stop.
Yeah.
Cisco recognized this,
But
which is exactly why they became a top 3 contributor to the open source project.
But the enterprise market is a completely different story.
Completely different. Most organizations don't have 50 software engineers dedicated strictly to network automation.
Right.
And that is why enterprise customers fall back to NXOS.
They want a unified toolkit.
Yeah, they want a single throat to choke when things break.
Right, where one vendor is responsible.
Exactly. They want vertical integration where the silicon, the optics, and the operating system are all guaranteed to work together.
That makes sense.
Plus, setting up a lossless Ethernet fabric using standard command line interfaces, it can easily require 50 lines of complex code per switch interface.
Oh, wow.
And if you multiply that across a multi-plane fabric with thousands of ports, human error is inevitable.
So NXS simplifies that.
Yeah, with NXOS, engineers can use tools like Nexus Dashboard to deploy point-and-click quality of service templates across the entire fabric instantly.
Okay, so you deploy the perfect multi-plane fabric, you install the smartest programmable silicon, and you unify it all with a pristine OS.
Sounds perfect.
But there is a literal physical wall hitting the AI industry right now that has nothing to do with code or latency.
No, it has to do with electricity.
Power.
Power is the ultimate bottleneck of the AI era. The source highlights data center labs that are fundamentally limited to providing just 4 kilowatts of power per rack.
Which is insane, because to put that into perspective, a single modern AI rack fully populated with high-end GPUs can draw well over 40 kilowatts.
Easily.
So we're seeing half-populated or severely underpopulated racks simply because the physical facilities cannot draw enough power from the grid.
Or pump enough chilled water to cool a full rack, yeah.
The presentation actually jokes about this, saying they are literally competing with the Teslas in the parking lot for the local power grid's capacity.
It's funny, but it's totally true.
Right.
And because you cannot physically build a giant centralized AI data center in one room anymore, the utility grids just can't support the concentrated load.
Yeah.
The industry is forced into this new trend called scale across.
Scale across.
Organizations are building geographically distant AI factories and engineering them to act as one single cohesive computing cluster.
This is wild to me. That's like trying to run a single computer where the CPU is in Chicago and the memory is in Dallas.
That's a great way to think about it.
How do you keep thousands of GPUs synchronized when the data has to physically travel hundreds of miles?
It requires a highly specialized class of networking hardware.
Okay, like what?
First, you need silicon with exceptionally deep buffers, like Cisco's P-series chips.
Because the data is in transit longer.
Exactly. You need a much larger waiting room on the receiving end to organize the packets as they arrive.
Makes sense.
Second, you are sending highly valuable proprietary AI models across public long-haul links. You have to encrypt that data.
But traditional VPN encryption requires CPU overhead.
Right.
Which adds latency.
Which is exactly why they use MACsec encryption, or IPsec. And MACsec operates at layer 2, right at the hardware level. It encrypts the data at line rate.
So the packets are secured as fast as the physical silicon can push them out, without adding that processing delay.
Exactly. And finally, you need the physical connection between the cities, which relies on advanced long-haul optics like ZR and ZR+.
How does ZR plus optics push terabits of data over those distances without losing the signal?
They use coherent optical technology.
Coherent optical?
Yeah. Instead of just flashing a laser on and off like a basic fiber connection, ZR plus optics manipulate the phase and amplitude of the light wave itself.
Oh, wow.
This allows them to cram massive amounts of data onto a single wavelength and push it across hundreds of kilometers.
Without needing those physical signal regenerators every few miles.
Right. And what's fascinating is that the physical lasers and receivers, the optics, are frequently the single most expensive line item on an AI network's bill of materials.
Wait, really?
Yeah, they often cost more than the massive 100 terabyte switches they are plugged into.
That is unbelievable. So you lay miles of fiber, you deploy these expensive ZR plus optics, you build a lossless Ethernet fabric with massive shared buffers. But at the end of the day, the network is just the highway.
Pretty much.
If it doesn't natively speak the exact same language as the highly specialized GPUs actually driving on it, none of that speed matters.
No, it doesn't.
And right now, the undisputed center of gravity in AI hardware is NVIDIA.
Everyone and their mother is trying to attach themselves to the NVIDIA ecosystem right now.
Which is why I want to push back a bit here. Let's separate the engineering reality from the marketing hype. Because a lot of companies just buy an NVIDIA system, slap their corporate logo on the metal chassis, and ship it to the customer.
They do.
So what makes this specific Cisco and NVIDIA partnership mentioned in the source material, an actual engineering achievement rather than just a marketing brochure.
The distinction is co-development versus reselling.
Okay.
Cisco isn't just reselling boxes. They are physically taking NVIDIA's native networking chipsets, specifically the Spectrum 4 and the upcoming Spectrum 6.
Right.
They are building the hardware around them and putting Cisco's NXOS operating system natively on top of the NVIDIA silicon.
Oh, I see. So it gives the enterprise customer the best of both worlds.
Exactly. They get the strict validated compliance of NVIDIA's reference architecture.
So they know the network will perfectly synchronize their expensive NVIDIA GPUs.
Right. But their network engineers don't have to learn a proprietary NVIDIA operating system. They get to use the Cisco command line interface and the Nexus dashboard they already know.
That's huge.
But importantly, they are maintaining GPU agnostic performance.
Oh.
While they offer that Spectrum integration for strict NVIDIA environments, Cisco's own Silicon One chips are running cutting-edge features to support custom silicon and ecosystems like AMD's Infinity Fabric.
Oh.
They utilize technologies like adaptive routing and direct data placement to guarantee maximum performance regardless of who manufactured the GPU.
Direct data placement is actually a massive leap in efficiency. How does that mechanism work?
Normally, when a packet arrives at a server, it has to be processed by the server's main CPU before being moved into the GPU's memory.
Right.
Direct data placement allows the network interface card to use PCIe to write the incoming data straight into the GPU's memory, completely bypassing the CPU.
So it's like a delivery driver walking past the front desk and handing a package directly to the person at their desk.
Exactly. It slashes latency. And they validate this agnostic performance by running rigorous benchmarks and uploading the raw results to the ML Commons Consortium for the entire industry to verify.
Wow. I just step back and just marvel at the sheer complexity of these networks.
It's hard to wrap your head around sometimes.
We're talking about dynamically spraying flowlets across multi-plane fabrics, utilizing MSC-SEC encryption over coherent ZR plus optics just to synchronize GPUs spread across different states.
It is an absolute engineering marvel.
Yeah.
But it actually introduces a really provocative thought when you step back and look at where this is all heading.
Quick, what's that?
Well, because these systems are so incredibly complex, organizations are relying heavily on AI agents to monitor the AI networks themselves.
Right.
So we are deploying highly autonomous AI agents to triage and self-heal the physical networks that are training the next generation of AI.
Yeah.
So what happens when the network's real-time routing decisions become too complex for a human engineer to even audit? If the agents hallucinate a network configuration, how long would it take us to realize the machines are building a network we can no longer understand?
That is, wow. That is a terrifying but totally valid point to leave everyone with.
Something to mull over.
That wraps up today's episode of the Systems Podcast.
If you enjoyed this episode, make sure to follow the podcast, leave a rating, and share it with another engineer or tech enthusiast.
And remember, great products are built on great systems.
We'll see you in the next one.